Take a moment, check over your warm-up, make sure it looks good. Now it's just a little quick review of your factoring methods from Chapter 4. Did anybody have any questions about those 4? So the goal of today is to factor again. We're going to factor polynomials of a higher degree. So what you're going to see today, with respect to what we've done in the past, most of the problems in the past, the degree, remember the degree is defined as the highest exponent you see in the problem. The degree we primarily took care of up in Chapter 4 was 2. Those were called quadratic equations. They made parabolas. And we factored to help us find x-intercepts on the graph. We're going to factor again in Chapter 5 to help us find x-intercepts of a graph, but the exponent changes. The degree of your polynomial gets bigger and bigger and bigger as we move through this particular chapter. So what do we need? Because the degree is going to change, we need additional methods to factor. So beginning with the end in mind, this little bit of vocabulary that we're going to go through here just has you quite simply answering the question, when am I done factoring? How do I know I'm done with this particular problem? And the answer to that question resides in our first vocabulary term of the day. The first vocabulary term is the term prime polynomial. A prime polynomial specifically is defined as a polynomial with 2 or more terms that cannot be written as a product of polynomials of lesser degree using only integer coefficients and constants, and if the only common factor of its terms are 1 and -1. That's a mouthful. You do not have to memorize that definition. You only have to be able to apply the definition. So let's talk about a for instance here. Our for instance is the polynomial 16x squared minus 4x plus 8. It's actually a counter example when I think about it. This particular polynomial, again, a polynomial is just an expression that has many terms. This particular polynomial is not prime because each of these terms is divisible by 4. So there's like a GCF in there. That's not a prime polynomial because it had other factors besides 1 and -1. So if you can pull out another GCF, and if you can use any of the other methods that we've talked about so far in our course, then that's not a prime polynomial. When something is factored completely, what we have, in essence, is a product of prime polynomials. So what you might see here in this example, x plus 2 times x squared minus 5x plus 6, that's not factored completely because this trinomial on the end factors again. It's not a product of prime polynomials. I love alliteration. Triple P, baby. Product of prime polynomials. Alliteration, is a second floor term, when all the words begin with the same letter. So you're done when you have a product of prime polynomials. Once again, this is kind of a counter example. X squared minus 5x plus 6 factors again. And they have it kind of off to the side here. X squared minus 5x plus 6, if we were going to go again on that, factors of 6 that make -5. Take a little shortcut there because I have an a value of 1 in this problem. Factors of 6 that make -5 would just be -3 and -2. All right, really I only have to teach you one brand spanking new idea today. And that big idea of today's lesson, I really only need your brain to pull in one more thing, is how to factor a sum and difference of cubes, not squares, cubes. It's super helpful before we get started to make a little list of some perfect cubes. Quite often, you get a little, homework quiz, or you might get a factoring test or something like that. I'll see students put their name on their paper and they make a list of perfect cubes right at the top. Pretty quick and pretty easy. You'll have your calculator if you're really struggling to come up with them. But right out of the gate, out of the new material that I'll have students sort of pulling into their brains, we got to talk about perfect cubes. So we'll make a little list first. For instance, 1 is a perfect cube. Because 1 times 1 times 1 is 1. 2 times 2 times 2 gives us our second perfect cube. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. And those are the ones I use the most. Have I gone bigger than that? Yes. Is there one on your homework quiz that I just made a little bigger than that? Also, yes. But you'll have your calculator. These are the ones that I need your brain to have ready access to. Just like you know the first 20 perfect squares by heart. You know, if I ask you, the square root of 49, you're like 7. You kind of just know those numbers. These are the 5 perfect cubes I need you to like pull into your soul. So maybe you're driving with mom or dad in the car a little later on, aunt, uncle, whatever special grown-up you have hanging around you these days. And you're just going to say, they might ask you how your day went. That's nice of them. Very considerate. You're probably like, it was fine. If you're anything like my children, like, okay, well, a little more detail would be lovely. I want to know how your day was. I do love you. But they were like, it's fine. What'd you do today? Nothing. Okay. Instead of answering nothing, maybe be like, I learned my perfect cubes. 1, 8, and just list them off real quick, 1, 8, 27, 64, 125. Just tell them that. Maybe tell them at like 4, 5, 6, 7, 8, 9, 10 times. Until, again, you've pulled those numbers into your soul. 1, 8, 27, 64, 125. Sounds like a little song. Maybe I should make a song for that. I don't know. But these are the numbers I need you to know for today. Okay? So that when you look at a problem, you quickly and easily recognize them. Do you see that? There's an 8. That's an important number. I've told you before, when I look at perfect squares, it's almost like they appear in a different font to me. Like, they just are important numbers. A math teacher is going to type them there for a reason. Same thing with 1, 8, 27, 64, and 125. They speak to me, my people. They're like, wait, you got to use a different method to factor this problem. And that's the method I'm going to teach you today. So a sum of 2 cubes specifically is defined as a sum, which means there's a plus sign in the problem. And then there's 2 cubes on either side of this plus sign. See that? That's how you know you have one. 2 terms. First off, there's a plus sign. And then you're going to see numbers like 1, 8, 27, 64, or 125 chilling in the problem. Maybe on either side of this plus sign. Okay, now, let's break this formula down a little further. To get the binomial in front, what we're going to do is not square root the first part and square root the last part. We're going to cube root the first part. That will give you the first term that you write down. So the cube root of a to the third is a. And then you would do that over here. The cube root of b to the third gives you b. And then to fill in the parentheses, and this actually makes a whole lot of sense. If we're trying to get back to a cubed, a times a squared, if you think back to yesterday's lesson when I multiplied, a times a squared would get me back to the a cubed. So I need to take my value of a and just square it. Then to get b cubed back out, I need 2 more b's on the other side. So I have to take my value of b and square it. And then to get the middle term, that's usually the trickiest one. What color should I use? I think I'm going to do orange. We just take our a and our b and we multiply them together. Last little bit is, see this plus minus plus? There's a little mnemonic device I have to help you remember the signs, and I think I have it written here somewhere. It's called SOAP, yeah. So let's talk about SOAP real quick. The SOAP method is designed to help you figure out what signs go in the parentheses when you're factored. So SOAP stands for same, O stands for opposite, and AP stands for always positive. So what you're going to see, back to our sum of two cubes formula, what we have in the original problem is a plus, right? Because it's a sum of two cubes. So the first symbol is the same. The second symbol, what's the opposite of a plus? Minus. So the second symbol is a minus, so that's opposite. And then this last symbol here on both of these formula is always positive. So same, opposite, always positive is how you get the signs in your answer. So let's try one. The first binomial is filled in for us, but I would go ahead and I'd cube root the first part, and that gives me x. I cube root 8, because it's perfect cube. The cube root of 8 is 2, because 2 times 2 times 2 gives me 8. If I think about what I need to multiply x by to get x cubed, I need 2 more x's. I need x squared to be in the first term. To figure out the last term, I got to ask myself, okay, 2 times what would get me back to 8? And that would be 4. And then to get my middle term, I just multiply these two things together. So that'll be 2x. X times 2 is 2x. And now I'm going to do my same, opposite, always positive. So to factor a sum of cubes, we cube root the first part, cube root the last part, and use same, opposite, always positive. Difference of two cubes works almost exactly the same way, except it's a minus sign. The formula is the same. You cube root the first part, and that gives you the first term in your first set of parentheses. You cube root the last part, and that gives you the last piece of your parentheses. You have to square A and square B to get your last term in the trinomial. And then we always multiply these two things together to get the middle term. Last part, same, opposite, always positive. So let's go ahead and take a look at a couple more. So the next example here is, do you see how I have an 8 and a 1? And I have an x cubed? That like jumps off the page at me. I'm like, oh my gosh, that's a difference of 2 perfect cubes. So again, to get the party started, we cube root the first part. The cube root of 8x to the third is 2x. And then I cube root the last part, and that's 1. I ask myself, 2x times what would get me back to 8x cubed? And that's 4x squared. And then I need to multiply 1 by 1 to get back to 1. To get the middle term, I just multiply 2x times 1. That's 2x. And then I do same, opposite, always positive. All right, we're at the point of the lesson where I shut my pie hole for a second and let you try. Ready, set, go. But yeah, you guys are rocking this so far. Nice job. So I see people cube rooting the first part, cube rooting the last part. The cube root of z to the third is z. The cube root of 125 was 5. You need 2 more z's to get back to z squared. You need 25 5s to get back to 125. To get the middle term, you just put those things together. So that's 5z. And then we do same, opposite, always positive. So same as your original problem. It was a difference of 2 cubes, so we put a minus sign in there. Opposite, always positive. You might have looked at that first problem and be like, Mrs. Lucas, you jerk. It's not a cube. What's step 1 in any good factoring problem? Yes, GCF. So that maybe gives you a little hint there. So this is also looking good. Mason did a nice job. I liked what he did there. He pulled out a 3y. And then you have 27y to the third plus 64. Both of those numbers are in our list of 5 numbers I'm asking you to pull into your soul today. 1, 8, 27, 60. I can't even talk. 1, 8, 27, 64, and 125 are your numbers of the day. So we would bring the 3y down. You know, you cube root the first part. That's going to give you your 3y. Cube root 64. It's going to give you your 4. 3y times 9y squared will get you back to your 27y to the third. 4 times 16 will get you back to your 64. And then 3y times 4, you got 12y there. And then you got same, opposite, always positive. Looking good, looking good. If you are concerned, remember you can distribute again. You should get the original problem back out 100% of the time. It does work. I promise it does. A couple more for some practice today. Make sure it's sticking. Okay, I'm liking this so far. People are cube rooting the first part, cube rooting the last part. So that's definitely going in. So this is 2x. And then if you cube root 64, that's 4. And then you have a trinomial. 2x times 4x squared would get me back to 8x cubed. 4 times 16 would get me back to 64. And then 2x times 4 gives me 8x. And then I got to do same, opposite, always positive. Natalie asked a really good question. She said, isn't this factorable? Oh my goodness, what did I forget to do? Who was first? Was it Faith? Maybe I just need to pass the lollipops around. I didn't notice it. Here's what's funny is that if you don't do it first, you have to do it now. So what I see in my answer, and this is funny because I'm recording this one, is I see a 2x and a 4 and a 4 and an 8 and a 16, and those are all even numbers. I'm like, oh my gosh, there's a GCF in here. So instead of factoring the GCF out at the end, yeah, step 1 in any good factoring problem, dose of my own medicine, I got to pull out a GCF. Jiminy Christmas. All right, so you might have pulled out the 8. I even walked around and I looked at you guys doing it too. That's so funny. So this is a little bit of a quicker way of doing it. You pull out the 8. Don't forget the 8 has to be part of your answer. So you have x plus 2, x squared plus 2x plus 4. Sorry about that, guys. Nice job. Alrighty. If you don't do it at the beginning of the problem, then you're stuck doing it at the end of the problem. It's a little more work to do it that way. But yeah, you could pull out the same, opposite, always positive. Hold up. Yeah, I'm doing it. I see it. Yeah, I got it. Same, opposite, always positive. But yeah, so then you're stuck kind of pulling the 2 out here. And then you got to pull the 4 out here. And then you'd have to multiply the 2 times the 4 to get your 8. But you get the same answer. You just got to factor again, which is a little irritating, but doable. So if you don't do it at the beginning, you got to do it at the end. Okay. Questions about sums and differences of cubes? That was like the really new thing I needed to teach you today. The rest of it is just the tail end of AC grouping. So a method that we've done before a little bit. Oh yeah, back to what Natalie was talking about. You got to ask yourself, is that factorable? It's not. When we factor a sum or difference of cubes, I know it's going to bother some of you, but there are no factors of 4 that make -2. This trinomial in the back is never factorable. Kids, if it were, I would have taught you a different formula. I'm not into tricking children. That is not what they pay me for, right? So if this were factorable, I would have taught you a different way to do the problem. Would have given you another tool. So this trinomial, what's so fun is that by the end, we suck chapter 4 into chapter 5. This produces imaginary solutions for us. So you would do the quadratic formula and get your complex solutions. That's a little later on when we actually use factoring as a method to solve for x. Remember, factoring is oftentimes just a means to an end, right? It's a technique we use for solving. So this goes somewhere. The idea is we use it to solve for x. This guy's going to push out our imaginary and complex solutions. Grouping is just the tail end of AC grouping. And you AC grouped to warm up today. You took A times C. You took your 3 terms, you split it into 4 terms, and then a lot of you just went like this in your warm-up. So to group it, you just group the first 2 terms together and the last 2 terms together, and you pull out a GCF. Why grouping gets taken up a notch in this chapter is because, I'll pull out the x minus 2, but then what I have left over is x squared minus 9. So what you need to be aware of is, you can factor using multiple methods in chapter 5. That's the new expectation, is that quite often you factor a problem once and you got to go again. You see what's hiding here? A case from your warm-up today, there's a difference of 2 perfect squares. So you actually have to factor this again. This is indeed not meeting our vocabulary for being a product of prime polynomials. X squared minus 9 can be broken down into 2 things that multiply to give us that. So we got a square root method on this first part and this last part here. So the x minus 2 is a factor, but x squared minus 9 factors to be your x plus 3x minus 3. And now it's a product of prime polynomials. I can't take anything else out. No GCF, no perfect squares, no AC grouping. That is done. So these last couple problems of the day have you using multiple methods to factor. I just posted your answers to your independent practice up there. Maybe you went ahead and tried to AC group number 3 because that's the technique that we quite often use there. You could also use a little guess and check on that guy. But yeah, you have x squared minus 9, x squared minus 5 as your initial go-to. X squared minus 9 breaks down to x plus 3x minus 3, and then x squared minus 5 doesn't factor anymore. Keep going on that one. Good. And then that's the only thing that's going to factor because it's the difference of 2 squares. There is a little, like I was saying, I did a little AC grouping in my head on number 3 to post your answer, but we can talk about that. If you do 1 times 45, that's 45. Things that multiply to give you 45 that add to negative 14 are negative 9 and negative 5, but you have to attach an x squared to those because your middle term is x squared. So when you go to set this up, you have x to the 4th minus 9x squared minus 5x squared plus 45. And then you group it. So that's a little behind the scenes work there. That's how I started getting that line right there. So the difference on this, it is just AC grouping. Anytime you have 3 terms, you can AC group. But watch how you rewrite that middle term. Make sure the exponent comes along for the ride. It's not there for decoration. All right. That is all the factoring I have to teach you in this course. We are done. learning the factoring. Now, you don't really learn it in class, right? You got some homework to do to get a little bit of practice. So let's go ahead and talk about that.